This is part 3 of a series of videos about compilers and the compilation of computer programs. The second stage of compilation is known as syntax analysis, the purpose of which is to discover any syntax errors in the tokenized program. Syntax errors are those in which the rules of the programming language have been broken. For example, in Visual Basic, an if construct must include the keyword endIf. The keyword for must have a matching next. A concatenation operator must be followed by something to concatenate. Double quotes must come in pairs, and so on. The syntax analysis of a tokenized program is also known as parsing, so another name for the syntax analyzer is the parser. Analysing the syntax of a program is rather like checking that a sentence written in plain English makes grammatical sense. With an English sentence, this can be done by examining the relationships between its constituent parts, a process known as parsing. This sentence is valid because it conforms to a particular formal grammatical structure. It contains a subject, the cat, a verb, sat, and an object, the mat. Needless to say, there are lots of formal grammatical structures, but let's stick with this particular one for the sake of discussion. This sentence is grammatically correct too, because it has the same valid structure as the first one. And so is this. Without context, this last sentence might seem rather silly. But who's to say that a cow can't jump over the moon? It conforms to a grammatical rule which doesn't concern itself with context and meaning. Before we can apply the grammatical rules of a programming language to a tokenized program, the grammar of that particular language must already be defined somehow. It needs to be written down in such a way that it can be communicated between programmers and, of course, the programmers who write compilers. It's important that there is no disagreement about what is and what isn't allowed. The definition of a programming language is normally done using a formal system known as a context-free grammar. Backus-Naur Form, or BNF for short, is a widely adopted notation for describing context-free grammars. Here you can see BNF notation being used to describe the legal syntax of an if construct in our simplified variation of BASIC. The vertical bars separate optional forms of the if construct. These optional forms are known as productions. Our particular code fragment is valid according to the second optional form of this grammar. The keyword then must be followed by statements, which in turn are followed by the keyword endIf. The terms in angle brackets also need to be specified using the same sort of notation. For example, in this particular language, a condition is defined as two expressions with a relational operator in between them. In turn, a relational operator is defined as one of these symbols. The definition of an expression is a little more involved. An arithmetic expression can include a variety of arithmetic operators and parentheses. To cater for short simple expressions and very long complex expressions, an expression can be defined recursively, that is, with reference to an expression. Here you can see an expression is defined as an expression plus a term, or as an expression minus a term, or a term. A term can then be defined recursively as a term multiplied by a factor, or as a term divided by a factor, or just a factor. And a factor is defined as a number, an identifier, or an expression in parentheses. Yes, this definition of an expression looks rather complicated at first, but don't forget, there are endless possible combinations of variable names, numbers, arithmetic operators, and parentheses that can make up a valid expression, and we need to cater for them all. For the definition of the if construct to make sense, statements needs to be defined, and so does statement. Notice again the recursive definition that tells us statements is a statement followed by statements. A typical programming language includes a wide range of statement types: if statements, for statements, while statements and the like. In this language, an assignment is also a type of statement. And an assignment is an identifier followed by an equal sign and then an expression. As you know, some languages require 2 equal signs for an assignment, not this one. Our definition of an assignment must allow a string literal to be assigned to an identifier, as in description equals freezing. So in this grammar, an expression can also be a string literal, which we can take care of by enhancing our definition of a factor. Of course, an arithmetic expression that involves a string, or a variable containing a string, is most probably illegal. Needless to say, this grammar also needs to make it clear what an identifier looks like. Here, it's defined as a letter or a letter followed by a combination of letters and digits. Another definition that defines an identifier recursively in terms of itself is an efficient way to do this. Think about it. This means that in our language, a variable name can't start with a number or contain spaces. Letters and digits, of course, need to be defined. A number also needs to be defined. This language allows for reals and integers. In this language, a string literal is a character or a group of characters inside a pair of quotes. So it could be defined like this, leaving us with the task of defining a character and a group of characters, and of course a quote. With so many elements defined in terms of other elements, you can see how complex even the simplest grammar definition might be. All of this is necessary just to cater for our simple code fragment. A syntax analyzer for a particular programming language would normally implement the relevant context-free grammar within the logic of its code as a set of recursive or hierarchically organised procedures. Let's be clear, BNF and its extended form are not used by compilers. They're a way of communicating grammars between programmers. However, if you happen to be writing your own compiler, there are several software development tools available that will write a parser for you if a context-free grammar is input using a formal notation like BNF or extended BNF. The first job of the syntax analyzer, that is, the parser, is to construct a data structure known as a parse tree. The parse tree, with all its nodes and branches, is a particularly appropriate intermediate representation of the various structures and constructs of a high-level program. Behind the scenes, the parse tree is a temporary, memory-based structure in which each node might be implemented as an instance of a class. The parser examines each token from the lexical analyzer in turn, paying particular attention to what kind of token it is. Each token is analysed programmatically. It is subjected to a succession of procedure calls which have been designed to implement the grammar. The token information is then inserted into the appropriate place in the parse tree. Of course, while this tree is being built, the parser is checking that the syntax of the language has been used correctly in the source code. For example, if the keyword if is not followed by a valid condition as defined by the grammar, or the endif keyword is missing altogether from the token sequence, then an error message will be generated and the compilation will fail. The parser can also check that the names for identifiers are legal. For example, that a variable name starts with a letter, and that parentheses and quotes have been used in matching pairs. A so-called recursive descent parser will build the parse tree from the top down, but there are other tried and tested approaches that could be employed. In reality, a parse tree, just for our simple code fragment, would be somewhat larger than the one illustrated here. For example, the representations of the identifiers and string literals in this parse tree have been simplified. A parse tree is also known as a concrete syntax tree, because it contains pretty much all of the information supplied by the lexer, along with grammatical definitions of tokens identified by the parser. If you examine the leaf nodes of this tree, you can see our original code fragment amongst all of this syntactic clutter. The syntax checking performed during the construction of a parse tree is limited. It's like checking that a sentence written in English begins with a capital letter and ends with a full stop. Analysing a sentence written in English for meaning is known as semantic analysis. The semantic analysis of source code is also an important job for a compiler. Although semantic analysis is somewhat more complex than simply making sure that keywords have been used appropriately, it's often thought of as another aspect of the syntax analysis phase. During syntax analysis, a compiler can spot problems like undeclared variables, multiple declarations of a variable within the same scope, misuse of reserved identifiers, attempting to access a variable that is out of scope, trying to assign the wrong type of data to a variable, the so-called type mismatch error, passing the wrong type of data as a parameter to a function or a procedure when it's called, a function's return value not matching the specified return type, arithmetic operators that don't operate on numeric types. You can't multiply one string by another, for example. The condition in an if statement not evaluating to true or false. The exit condition of a loop not evaluating to true or false. Depending on the source code language, semantic analysis can be a big job indeed. The parse tree must now be refined to become an abstract syntax tree, containing only essential information. A lot of information that was important for parsing the token stream can now be discarded. Token classes are no longer needed. Quotes, delimiters and parentheses can all go too. The abstract syntax tree is a much more compact representation of the source code that makes it easier to analyse and process further. In fact, building a parse tree is relatively simple given the grammar, which is why there are plenty of off-the-shelf programs available that can build parse trees, and these programs can be incorporated into a new compiler. Building an abstract syntax tree, on the other hand, is not trivial. The compiler programs that do this need to be much more in tune with the nuances of the language that the source program has been written in. Some compilers will construct an abstract syntax tree directly without first constructing a more explicit parse tree. Once the abstract syntax tree has been built, it is traversed, perhaps several times, to perform a detailed analysis of the variables and indeed of any other names that were used in the source code, such as constants, arrays, functions, procedures, parameters and classes. With source code written in C++ or VB.NET, for example, all variables must be declared by the programmer before use. So type information is readily available in the symbol table to check the validity of expressions. When an identifier is referenced, the symbol table is consulted to make sure the identifier is known and properly used. Information derived from the abstract syntax tree is used to update the symbol table. Various attributes might be stored depending on the nature of the identifier. For constants and variables, the data type, data size, initial value and scope might be written into the symbol table. For an array, the number of dimensions and the array bounds might be stored. And for subprocedures and functions, information about their arguments and return values can also be stored. For some identifiers, the compiler can examine their types and calculate how much memory they need in advance. This also allows the compiler to allocate runtime memory addresses at this stage. Other compilers will do most of the memory allocation later, during the code generation phase. For local variables and parameters, these memory addresses are offset based, relative to the start of the program's execution stack. For other identifiers in the source code, such as dynamic array variables, the exact amount of space can't be known by the compiler in advance, so memory has to be allocated dynamically, that is, at runtime. Dynamically allocated identifiers are usually assigned to an area of memory known as the heap. Of course, exactly where variables reside in physical memory when the program is running is actually up to the operating system. Because the symbol table will be frequently accessed and modified during all stages of the compilation process, it needs to be implemented as a data structure that allows for very fast access. For this reason, the symbol table is usually implemented as a hash table. Each symbol can be used as a key for the hash function, and its various attributes can be stored in the hash table either as a record or as properties of an object. Some compilers implement the symbol table as an ordered linear list, which can be binary searched, while others might employ a binary search tree. In many programming languages, the symbol table is a temporary data structure that exists only during compilation. However, in other languages, the symbol table may persist beyond compilation and be used by the object code for debugging purposes. Some compilers don't use a symbol table at all. With an object-oriented approach to compiler design, each node of the abstract syntax tree can contain any amount of extra information, including all of the information that might otherwise be stored in a symbol table. Symbol table or not, it is during the construction and multiple traversals of the abstract syntax tree that most semantic errors will be found. Source code often contains mathematical expressions that involve several arithmetic operators, and parentheses to control the order in which the operations are performed. For example, the source code might contain an expression like this one. This is the normal way of writing an arithmetic expression. It's called infix notation. Each operator is written in between the values or the variables that it will operate on. The parentheses are essential here to indicate the addition operation should be performed first. It's not easy to generate machine code from a complex expression with lots of parentheses in it, so a compiler might attempt to represent an expression like this without parentheses, and there are several ways it can do this. A mathematician called Jan Lukasiewicz invented an alternative way of writing the same expression without the need for parentheses. This is called prefix notation. It's also known as Polish notation because he came from Poland. Each operator is written in front of the pair of values it will operate on. This is called postfix notation. It's also known as reverse Polish notation. Here, an operator follows the pair of values it will operate on. An arithmetic expression can also be represented unambiguously using a special form of binary tree known as an expression tree. Here's an equivalent expression tree. Notice the absence of parentheses. Many compilers will employ this particular intermediate format. A compiler can create an expression tree from an infix expression in the source code programmatically using stack data structures. Once built, a post-order traversal of the expression tree will give the reverse Polish form. Some compilers use graph data structures to represent arithmetic expressions. To be more specific, directed acyclic graphs, otherwise known as DAGs. Here's a complex expression and a matching expression tree. With a directed acyclic graph, an operand need only be represented once, even if it occurs multiple times in an expression tree. Notice how the A occurs twice in this expression, but only once in the graph, with two edges to its parent node, the plus sign. Also, common sub-expressions need only be represented once, like b minus c in this example. Directed acyclic graphs not only represent expressions more succinctly, but they also give the compiler important clues about how to generate efficient low-level code. To summarise, syntax analysis checks that the rules of the programming language have been followed correctly. Syntax can be defined using a context-free grammar. Backus-Naur Form is a well-known notation for communicating the grammar of a programming language. Grammar is applied programmatically to build a parse tree. The parse tree is then refined to become an abstract syntax tree. The abstract syntax tree is traversed several times during semantic analysis. The symbol table is frequently accessed and updated during this process. The symbol table is often implemented as a hash table for speed of access. Polish and reverse Polish represent expressions without parentheses. Expressions can also be represented using trees or directed acyclic graphs. Of course, a compiler can't spot everything that might be wrong with a program. A variable might exceed its space allocation at runtime, for example, or a circumstance may arise in which the exit condition of a loop is impossible to meet. Error traps in the source code are needed to catch runtime exceptions like these. Furthermore, a compiler doesn't know if the postage and packaging costs should be added or subtracted from an order total. Only thorough testing can deal with logical errors like these.